Thank you, Martin, for the introduction. Thanks to Martin, Annetta, and Lorenzo for the kind invitation to join you on Zoom. So let me talk to you about a recent joint project. This is with Christin Bibby at Louisiana State, Nir Gadish, who just joined at Michigan as a postdoc, and Claudia He Yun, who's at Brown University and who is graduating this year. Okay. And so let me give you background. This is going to be a talk on applications to the topology of a very well-known class of varieties, namely the moduli space, which I'll denote MGN. This is a moduli space of genus G, n-marked algebraic curves. We'll work over the complex numbers throughout. So there I drew you a cartoon picture. When I say algebraic curve, I mean smooth and proper and irreducible. So this is the same as a Riemann surface, so a one-dimensional complex manifold with n distinct labeled points, labeled 1 through n. And this is the space that's the main character of this talk, and probably of talks of many geometers and some physicists too. So we will take advantage of the fact that MGN is not just any space, it's algebraic, it has algebraic structure. You may view it as a variety or scheme. More precisely and important for our purposes will be to view it as an orbifold or a Deligne-Mumford stack. Whatever it is, its dimension is actually known and goes back to this calculation, goes back even before the space MGN was constructed formally as a stack over spec Z. So this calculation is old. The complex dimension of MGN is known to be 3G minus 3 plus n. But the geometry of MGN, I think it's fair to say, is a sort of persistent but interesting mystery occupying the attention of many geometers. So our goal will be to study the rational cohomology of MGN. Maybe I should remark that this is equivalent to studying, so for those who are more inclined towards arithmetic groups and related groups, this is the same as studying the rational cohomology of the mapping class group. So maybe I should write mod GN. And that comes from the interpretation of MGN as a quotient by the action of a mapping class group of a contractible space called Teichmuller space. Okay. But for us, the algebraic structure will be paramount, will be very useful. Let's review. So one thing that we could study prior to studying the individual cohomology groups is, of course, the Euler characteristic. Recall, it is the alternating sum of the dimensions of the cohomology groups. So here I wrote down the definition. You can see that it is an integer, since it's alternating sum of dimensions of vector spaces, rational vector spaces. And there's beautiful work on this. So what I wrote here is, let me explain it in 2 steps. This is a formula obtained by Zaggy, Bini Harer. It's an exact formula for the orbifold Euler characteristic of MGN. So that's a formula that takes into account sizes of stabilizers along certain positive codimensional strata. And this orbifold Euler characteristic is exact. It's an actual Euler characteristic for n sufficiently large. So in this formula, I mainly want you to agree that it's beautiful. The B sub 2G is the 2G Bernoulli number. So certainly one expects some beautiful structure in this space based on this calculation itself. Now, let me say something quote unquote obvious, which is that there's a action of the symmetric group Sn on n letters on the space MGN, namely by permuting the labels of the marked points. So one should study everything possible Sn equivariantly. In particular, the Euler characteristic itself ought to be promoted from a number to a virtual Sn representation. So an element of the Grothendieck group of Sn representations. All I mean is the following. Let's consider the Euler characteristic Sn equivariantly. So you consider it as a sum of the ith cohomology groups with rational coefficients of MGN. So here, this is Sn is a finite dimensional representation of the symmetric group, just because Sn was acting on the original space. And this is to be interpreted as a formal sum of symmetric representations. Recall that there's a finite list of, up to isomorphism of irreducible representations of Sn. I'm working in characteristic 0 here clearly. So there's an irreducible representation for every partition, as in here. So for every partition lambda of n. So this is what I mean by virtual Sn representation. After decomposing into irreducibles, one can just remember the numbers C sub lambda. These are integers, positive, negative, or 0, which record the virtual multiplicities of the corresponding irreducible representations that I've written V sub lambda. So that's the definition of Sn equivariant Euler characteristic. This has nothing to do specifically with MGN, it's just a completely general setup. But that's what we should study if indeed we do have Sn actions on our spaces. It's convenient, I mean, it's more than convenient, but it is convenient to record a virtual Sn representation as a symmetric function of degree n. Let me remind you, blackboxing a lot of stuff, how this goes. So here I'll let this lambda be the ring of symmetric functions. So, recall that these are power series of bounded degree in infinitely many variables, x1, x2, x3, and so on, that are symmetric under permuting any finite set of indices. That's lambda, and this has a grading by degree. So I'll write lambda sub n here for the degree n homogeneous part. And then I'll just assert to you, in case this is just in case this is new information, we'll assert that lambda n has many famous canonical bases, just as a vector space. For example, it has a basis of Schur functions. So there's a symmetric function denoted S sub lambda for each partition lambda of n. This is a generating function for semi-standard tableau of shape lambda. Whatever it is, just notice that there's one for every partition. So therefore, right, so the point is, if you have a virtual representation, you can encode it simply as the sum of the appropriate Schur functions. So that single symmetric function remembers all of the integers C sub lambda. Okay, moreover, if you have a natural sequence of Sn representations as n ranges, 0, 1, 2, and so on. So here I'll fix G at least 2, just for expository ease, so I don't have to deal with special cases. Then just add up formally all of the individual symmetric functions that we discussed in degrees 0, 1, 2, 3, and so on. So in other words, you can encode all of these virtual S0, S1, S2, S3, et cetera representations by a single symmetric function with unbounded degree. So formally, this isn't an element of lambda itself, but it's an element of the degree completion. So here, this lambda hat denotes the degree completion of lambda. And this whole gadget, this one sort of symmetric function with unbounded degree, is called the Frobenius characteristic of this S module, that is to say, this sequence of Sn representations, or virtual Sn representations. For the purpose of this talk, you can regard it as a data structure that remembers these representations. So finally, I can at least report to you that in a 2013 paper of Gorski, he obtains a sort of Sn equivariant promotion of the previous result of Bini-Harer. So in other words, not just the Euler characteristic of MGN, but the Sn equivariant Euler characteristic of MGN, which is expressed as a formula for each fixed G at least 2 of this Frobenius characteristic. And the formula is very long. I should have taken a screenshot, but he didn't have it all put together in one beautiful slide, so I didn't. In any case, it's not the main focus of the talk, though it did inspire the next section that I'll discuss now. Okay, so there's some remarkable sort of geometry underlying these spaces, to say the least. Okay, so the focus of our talk is on a refinement, namely with respect to Deltagn's canonical weight filtration. And again, this is, key in this story is the fact that MGN is a variety. For any variety over the complex numbers. So in particular, this variety need not be smooth nor projective, although that case is the case of sort of classical Hodge theory. For any variety, the rational cohomology of that variety was shown by Deltagn in the 70s to carry some extra structure called a mixed Hodge structure. Part of a mixed Hodge structure is the data of a weight filtration. So I'll write W naught through W2I for Deltagn's canonical weight filtration on the rational singular cohomology of a variety over the complex numbers. This weight filtration has many important properties. The one that, so let me just assert to you that the weight J graded piece, which I'll denote as shown. So by definition, this is the Wj quotiented out by Wj minus 1. So the associated graded of the weight filtration. Is shown by Deltagn to naturally carry a pure Hodge structure of weight J. And there's a lot more to say here. That pure Hodge structure is in fact induced by a single Hodge filtration. So a single decreasing filtration on the cohomology groups. So you should think of this as a sort of generalization to the not necessarily smooth and projective case of Hodge structures. This is part of the data of a mixed Hodge structure. The weight filtration is compatible with lots of natural geometric constructions. For example, it's compatible with Poincare duality. So here, let me assume that X is smooth. I'll just assume it's irreducible for ease. Let's let D be its complex dimension. Then here, I'm asserting that the weight filtration is compatible with Poincare duality. So the weight J graded piece is of the degree I cohomology is Poincare dual to the weight 2D minus J, degree 2D minus I, compactly supported cohomology of the variety. In particular, since there's no compactly supported cohomology below degree 0, then if you believe this Poincare duality assertion, there's no cohomology above weight 2D. And that's why we, well, conversationally refer to the cohomology in weight 2D as the Topweight cohomology. This is a canonical quotient of the rational cohomology of X. And again, this is a Poincare dual to the weight 0 compactly supported cohomology, which some experts probably rightly seem to view as more natural to study. So when I talk about the top weight, say, Euler characteristic of MGN, I mean the alternating sum of the top weight cohomology groups. So here, in this notation, this is already viewed, again, as a, say, virtual SN representation. So again, these are SN representations because SN, the action of SN sort of goes through all of these identifications. So here, when I talk about top weight Euler characteristic, you can view it either as a virtual SN representation or just compute dimensions and get a single integer out. And here D is just the dimension of MGN, so 3G minus 3 plus N. Okay, so let me just show you for fun, I guess, for fun and for context, a formula for the top weight Euler characteristic of MGN. So it's sort of a top weight analog of Gorski's formula, obtained in joint work with Faber, Galetius, and Payne recently, or fairly recently, I guess. So this is a formula for, fixing. So let's fix G at least 2 again. There are results for G 0 and 1, but they look different. This is a formula for the Frobenius characteristic of the top weight Euler characteristic of MGN. It looks like this. And remarkably, this formula was conjectured by Zaggy in 2008. So what happened was Faber was able to compute this these Frobenius characteristics for G up through 8, so for G from 2 through 8, and showed this data to Zaggy, who then produced this conjecture, which seems remarkable to me. And this is so we were fortunately equipped with the conjecture, which we were then able to prove using the perspective of tropical geometry. I should probably say just a few things, so that we can properly admire Zaggy's conjecture. So there are Bernoulli numbers here. And they arise in the formula because of its reference to orbifold Euler characteristics of tropical moduli spaces. Now, in one sense, so I was supposed to write down a completed symmetric function for you. So in what sense have I done so? Well, there are these terms capital P that I put in pink that I haven't defined for you yet. So here, first let me define little p. This is a little piece of I for a non-negative integer I is the ith power sum symmetric function, just the sum of the ith powers of all the variables. You can see that this is a symmetric function. It's invariant under permuting indices. And capital P, is defined to be 1 plus little p. So in that way, I have told you a symmetric function, an element of the degree completion of the ring lambda. But there's a lot to unpack here, certainly. Okay. Oh yeah, and then if you're just interested in the numerical shadow, then you can extract it as a corollary of our theorem. So the numerical shadow, at least for n at least g plus 1, so for n sufficiently large, gives this formula for the top weight chi of mgn, again, depending on a Bernoulli number. Any questions or comments? Okay, so this talk is about the case genus 2. So first, let me explain why we're studying genus 2. I've been obsessed with this for actually quite a while. So first, in the case g equals 2, I've just written out what the Faber-Zaggy formula says. So again, this is some symmetric function. It's infinite. It occupies infinitely many degrees. That might not be sort of so visible, but remember that these capital P's, right, so capital PI is 1 plus little pi. So if you have something like 1 over capital PI, that should be interpreted as whatever it's supposed to be. And so on. So this is the way in which this really tells you about all the n's at once for fixed g. Okay. And if you want the numerical shadow, then, sorry, this is the top weight chi. Just as a number, it's for n at least 4, it's up to sign is n factorial over 12. That 12 here is this 12 over there, it's a Bernoulli number, and is also the number of automorphisms of the theta graph, which will play a role, a starring role shortly. Okay, so this numerical, this was sort of recovered in a paper of mine on tropical moduli spaces in genus 2, but it's a numerical shadow, something that Faber knew in unpublished work, which is the work, exactly the work he showed Zaggy in order to produce this remarkable conjecture. Okay. So, okay. How are we to study the top weight cohomology of MGN? So this is a story that I've probably told many times. So apologies if there's any repetition for you. The main comparison theorem that we're using is a comparison theorem that relates up to a degree shift the top weight cohomology of MGN with the reduced homology of a combinatorial space, delta GN. This is the tropical moduli space of curves of genus G with n markings. This identification is, in a sense, contained in the work of Deltagn already from the 70s on mixed Hodge structures. But the identification of this tropical moduli space of curves with the boundary complex of a normal crossing compactification of MGN was obtained in work of Abramovich, Caparasso, Payne. And you can see my papers with Galatius and Payne for some details. Yeah, okay, so I just wrote down that delta GN is the moduli space of genus G and marked tropical curves. And let me actually define this moduli space, or at least give you an indication of what it parametrizes. I think I left myself room. Yes, okay. So let me just tell you from the beginning, completely combinatorially, what is a tropical curve for us. So a genus G n-marked stable tropical curve, and I'll drop the word stable from henceforth. So it is, I want to make the real definition, but let me start by drawing a picture of one. So here's a typical tropical curve. So let me write a picture and then wave my hands at it. So it's some kind of vertex weighted metric graph with marked points. So let me write it out. So gamma is a graph. It's connected. Multiple edges and loops are allowed. There's a metric, formally a length function from the edges to the positive reals. There's a weight function. I put it in purple in the picture. So this is a non-negative integer weight for every vertex. And there's a marking function. So an assignment of the numbers 1 through n to the vertices. Now here, I've drawn the marking function in the traditional, per tradition, I've drawn the marking function showing the marked points as little half edges. Those are not actual edges of the graph. Just think of them as half edges or legs. This is, true to the non-Archimedean picture, but for the moment, combinatorially, I just have formally a map of sets from 1 through n to the vertices. Okay. So, and I have to say what all this satisfies. So first of all, the genus, which is defined as the first homology plus the sum of the weights is equal to G. And we have a stability condition, so such that for every vertex V, let's see, the valence of V plus twice the weight plus the number of marked points is at least 3. Sorry, I didn't write notes on this because I was like absolutely sure. But if I've made some silly error, please let me know. But this is a stability condition. So another way of saying what a tropical curve is that it is the dual graph of a stable curve in the sense of Deligne-Mumford-Knudsen plus a metric, a formal assignment of lengths to the edges. And let me require, in addition, that the curve has volume 1, meaning that the sum of the edge lengths is 1. Okay, so here on the right, I think I've managed to draw a tropical curve of genus 3. You can see the graph theoretic genus is 2, but I happened to write the number 1 in purple on one of the vertices. So sorry, genus G equals 3, and it happens to be 3 marked. Okay, and that's the full definition of a tropical curve. So now delta G, oh sorry, are there any questions or comments? Okay, so delta Gn is a combinatorial space whose points are in bijection with isomorphism classes of tropical curves. Let me define it sort of loosely. So here, the set of points is the set of stable tropical curves of genus G, so with n marked points. So I'll just write of type Gn. And this is up to isomorphism. And one can construct this space. Well, okay, one can define a topology on the space quite naturally. Maybe I won't do it too formally. I'll just maybe draw some pictures. So the pictures are as follows. So first of all, within a fixed combinatorial type of tropical curve, it's fairly clear how to topologize the choice of lengths. So if you have some picture like this, say this is a genus 2 0 marked tropical curve, then you want to build, inside your space delta Gn, you should see some simplex. The interior of a triangle parametrizing choices of A, B, C, such that A plus B plus C is 1. But you need to take the quotient by the action of the isometry group, or the automorphism group, the graph theoretic automorphism group of the theta graph. So here, this is a group. It's isomorphic to S2 cross S3 because you can flip the theta and interchange the edges. And this naturally acts on the space the interior of this triangle. The S2 doesn't do anything, right? But the S3 permutes the 3 coordinates of this standard simplex. So again, somewhere inside delta 2, 0, there is some kind of open triangle. And then you need some way of gluing these together. And roughly speaking, this is given by the combinatorial relation of weight contraction on edges. So, as an edge length approaches 0, so say B approaches 0, we want to contract the edge. Okay, so let me, I'm doing it in this example, but let me just do it in general. So if you have an edge length approaching 0, and the edge is a non-loop, joining vertices of weight W1 and W2 respectively, then in the limit, you pass to the tropical curve where the edge has been contracted to length 0 in the literal sense, and the sum of the weights is placed on the new vertex. There's a corresponding picture for a loop vertex. So if you contract a loop of based at a vertex of weight W, then the loop disappears in the limit and you increment the weight. And according to the rules above, you once again have a tropical curve of genus G. Okay, so that would be the way in which you sort of glue together these various quotients of open simplices. So I've done this a bit informally, but maybe you get the sense of a combinatorial space parametrizing marked vertex-weighted metric graphs. And this space was constructed, sorry, I didn't put any references, in the context of tropical geometry by Bernetti, Mello, and Viviani. With work of Caparasso about the same time being very relevant, and earlier work of Gatma and Markwig, especially in the genus 0 case. And then even earlier work, if you sort of think broadly, of Color-Voetman being very, very closely related. So this was their work from the 80s on a closely related space called outer space. So the idea of studying, parameter spaces for marked, for metric graphs actually goes back a ways into the realm of geometric group theory. Okay. So, yeah, and again, so just to recall, the reason we're looking at the space is because of the comparison theorem that is now at the top of the slide. Namely, its rational homology controls the Topweight cohomology of MGM. Okay, so why am I talking about the genus 2 case? That's it's the first one we don't, in some sense, fully understand. So delta 0n, the space of genus 0 n marked tropical curves. So these look something like trees of marked points. That's a typical genus 0 tropical curve here with 5 marked points. This space is classical in the sense of appearing before 2000, I'd say. So in work of Billera, Holmes, and Voetman, this space is studied under a different name. It's the space of phylogenetic trees on n-1 marked taxa. And it's known to be homotopy equivalent to a wedge sum of spheres of dimension n-4. There are n-2 factorial of them, I think. And not only that, so the minute you have a wedge sum of spheres, there's exactly one interesting homology group to study, for example, namely top homology. And one can and ought study it SN equivariantly, and this was done in work of Robinson, Whitehouse, from the, I can't remember the exact date, but I think the late 90s, they study the SN representation on the top homology of delta 0n. Delta 1n is actually also a wedge sum of spheres. This is a consequence of some stuff I did with Soren Galatius and Sam Payne. And one can also study the SN representation of on the top homology, the only non-zero reduced homology group of delta 1n. And this is also done by us, but it was done in completely different context and language, of course, by Getzler previously. It was actually not at all clear. I mean, one had to work, we did work to unite the two formulas. So we were able to study the SN representation and eventually rectify it with Getzler's formula. Okay. So yeah, I don't know what to say. There's this sort of miracle. I can't tell if it's a miracle or it's just that we usually are much better at studying spaces that are homotopy equivalent to wedge sum of spheres, but you often get this wedge sum of spheres, whether it's because of shellability reasons or otherwise. Delta 2n for me is the next case. It's the case when you don't have that sort of such simple sort of homotopy type. And I think things are a beautiful mystery still in the case G equals 2. So it's just to reiterate, in general, it's not a wedge sum of spheres. And the integral homology can actually have torsion, as I showed in an old paper. On the other hand, its integral homology, and hence its rational homology, is concentrated in top 2 degrees, the reduced rational homology. In general, for genus G, you have homology concentrated in top G degrees. And so this is the first time, yeah, I should have said, sorry, I was being a little bit unnecessarily mystifying in these first 2 cases. Okay, so the rational homology of these spaces, since it is concentrated in a single degree, knowing the rational homology is exactly to know the Euler characteristic. And the Euler characteristic was computed in previous slides, was known to Faber, Getzler, people like that. So these computations rectify with those as well. So again, then just to drive home the point, delta 2n is the first case where you don't know everything about homology due to knowing Euler characteristic, because the homology is concentrated in 2 degrees. So basically, you have some mystery difference between the dimensions of 2 homology groups, or maybe as a virtual SN representation. You know what the difference is, but you don't know them individually. This is the first case where Euler characteristic is not determinative. Sorry, is that logical structure clear? Okay, so that's why that is a reason to be quite interested in this. So this is a screenshot from an old paper. This just shows you, sorry, the notation is a bit old. This just means delta 2n. And this shows you computational results on the dimensions of the only non-zero rational homology groups, reduced rational homology groups. So I was able to compute this up through n equals 8 marked points. And just as a sanity check, you can look at these various pairs of numbers. And if you subtract, then you see that the difference is n factorial over 12, as was claimed before. So that's the Euler characteristic computation. So here, there's something really, like I want to unpack this mystery. So we understand the 86 minus 26 equals 60 quite well, but we don't understand the 86 and the 26 individually quite as well. This is an interesting sort of new sequence of SN representations to be studied. And I should mention that the results that are here in this table were superseded by work of Claudia He Yun appearing recently, which sort of makes SN equivariant the data in this table. So that was hard computationally. A similar approach, namely a cellular approach, was used, but she had to sort of do some clever tricks involving some projection formulae to actually compute. I had been able to do this for up to n equals 8 points just numerically, and to be able to get to that same threshold SN equivariantly required some tricks from representation theory. Okay. So that is also old news. So the point of this talk is to discuss computations that supersede both of these papers. And this is the work that we did joint with Christin Bibby, Nir Gadish, and Claudia He Yun as well. I should mention, so Christin and Nir are experts in many things, including configuration spaces on graphs and representation stability phenomena. And we'll see the connection shortly. So let me just give you a flavor of the computations we were able to obtain. So for n up through 10 marked points, we're able to completely get these representations SN equivariantly. So here you see, like for n equals 10, for instance, you see various coefficients attached to various partitions of 10. And there's only one group listed for each n, because the Euler characteristic formula tells you how to get the other one just by subtraction. I hope that's clear. So that's what we're able to do completely. And then for more marked points, we don't have the full representation, but we're able to get some pretty good partial data. So up through 17 marked points. So those are the main theorems that I wanted to present. And now I'll tell you about them, and I'll tell you about the connection to configuration spaces of graphs. But first, let me see if there are any questions or comments. Okay. Yeah, okay, so let me tell you the proof, or how we obtain these computations. So the sort of secret weapon here is a contractibility statement that is in one of my papers with Soren and Sam. It says that a certain subspace that I've noted delta GN bridge, BR for bridge, is contractible. So by definition, this is the closure of the locus of parametrizing tropical curves with a bridge edge. What's a bridge edge? It's an edge in a connected graph such that removing it disconnects the graph. Okay, so that is a fairly, like that's a big locus, basically, especially from the perspective of computations. Let's discuss what kinds of tropical curves are in the bridge locus, delta GN bridge. So for example, if you have a curve with a positive weight, positive vertex weight, like this is in the bridge locus. So sorry, so these are just pictures. Let me label examples of tropical curves in the bridge locus. So anytime you have a positive vertex weight, you're in the bridge locus. Why? Because you can shoot off that weight and remain stable. So something like this specializes, right? So, sorry. So I'm trying to draw a picture on the right that justifies that the picture on the left is in the closure of tropical curves with bridges. So as that bridge on the right goes to length 0, you get the thing on the left. Therefore, the thing on the left was in the bridge locus. Okay. Same with anything with a cut vertex. So anything with a cut vertex is in the bridge locus because you can expand the cut vertex into a bridge. So positive weights and cut vertices. Certainly if you have a bridge, you're in the bridge locus, but I'm saying that this is more than that as well. Repeated marking. So by a repeated marking, I mean a situation where the marking function is not injective. So you might have 2 marked points sitting on the same vertex. So this is also in the bridge locus. Oh, sorry, I'm having some issue here. Oh, there we go. Okay, so yeah, so anything with a repeated marking is in the bridge locus because you can shoot the repeated marking off and you still have the stability condition holding. So I'll just draw it for you and then I think you'll be convinced. Like that. So all these things are in the bridge locus. Is that okay? That's the third one that's conceptually the most important for us. You see, like if you took a random tropical curve in some fashion with 1,000 marked points on genus 2, what you would see almost surely is a very, very complicated tree structure on the 1000 marked points coming off of some genus 2 curve in some fashion. So most of tropical moduli space looks like this. But what we show is that that all lies in a large contractible subcomplex. Okay, so what's left? In other words, what's in the complement of the bridge locus? Well, given what we've said, and again, sorry, I'm assuming that G is, let's say, at least 2 here.
Say a word as to why the bridge locus is contractible, or is this too difficult to explain in a second?
No, let's see. I could, but I forgot. So
okay.
I can tell you approximately. I mean, so we run an argument that's like reminiscent of discrete Morse theory, though it is not exactly discrete Morse theory. And Claudia He Yun is in the process of writing a paper that defines and carries out discrete Morse theory of symmetric delta complexes. But I will tell you, there's a lot for her to do, because the kinds of deformation retracts that go on in CGP can do things like take a triangle and just crush it down to one of the edges. And that is not an elementary collapse in the sense of discrete Morse theory, which only allows sort of collapsing along codimension 1 faces. So there's something to rectify there, which is current work of Yun. But in any case, you define some sequence of deformation retracts. Let's see, and it has something to, I mean, it's like, I give you a sort of impressionistic view, which has something to do with, if you're in the bridge locus, then you can sort of start, and I need to tell you deformation retract. So you're sitting somewhere in the bridge locus, you need to walk somewhere. And where you walk is by sort of lengthening bridges in an appropriate sense, until some of the non-bridges sort of pop out of existence, because you're preserving the volume 1 condition throughout. So it has to be made precise. One of the main things to make precise is the fact that you can sort of do such lengthening in a well-defined way. So that's codified in the paper of mine and Sam and Soren's, the one whose title starts with marked points, is the notion of properties of vertices of the symmetric delta complex. And I admit, I sort of thought when talking to Claudia initially that this was going to be some sort of mild variant of discrete Morse theory in the context of what we've called symmetric delta complexes. Sorry, so just to back up for a moment, by that I mean some kind of simplicial complex type structure, except with self-identifications allowed on the simplices, as we already saw in the example of a theta graph. But it turns out there's more to rectify. It's not exactly discrete Morse theory going on. Yeah.
Okay, thanks.
Okay, great. Okay, so what's left? Like, what is in the complement of the bridge locus? I almost wish I could just pop quiz the audience. I mean, the only thing that you have left is you have an honest genus G metric graph of total edge length 1 with distinct marked points running around. They can't collide because then you'd be in the repeated marking locus. They can't branch off in some tree structure, because if you look very carefully at a tree, if you look at a leaf, that leaf must support at least 2 marked points in order for stability to hold, the stability condition to hold. So there are never any non-trivial tree structures in the marked points. So again, what's left is the locus of 2-edge connected. That's not that important, but we already showed that we don't have to deal with cut vertices. So 2-edge connected volume 1 metric graphs of genus G, together with n distinct markings. And this whole thing is taken up to isomorphism of the marked metric graph. Now, contractibility of the bridge locus means that what I'm really studying is the 1-point compactification of the space I've drawn in big brackets here, if I wish to study the topology of delta GN. And so that's why compactified configuration spaces of graphs enter the picture. And I'm very happy about this, because I've sort of was obsessed with, as a sort of tourist, with configuration spaces of graphs for a while. Oh, sorry, I've gotten ahead of myself. So in the case of genus 2, it turns out that there's only one genus 2 graph with no cut vertices, and it's the theta graph. And the fact that the theta has 12 isomorphisms is somehow showing up as a Bernoulli number in Faber's formulas. So again, the complement of the bridge locus in genus 2 is the set of tropical curves of isomorphism with n distinct mark points on a theta. So we're very close to studying the configuration space of n distinct points on a graph theta. It's not quite the same simply because, like, again, this is passing between moduli spaces and configuration spaces. This is exactly passing, taking isomorphism or, taking isomorphism classes. So what's the connection between the configuration space denoted conf sub n? Maybe I'll write it. So this is the configuration space of n distinct markings, marked points on the topological space in question here, theta graph. Yeah, so if I want to give you a tropical curve as in the picture here, I need to do a few things. I need to tell you 3 edge lengths, A, B, and C, that add up to 1. That's an open triangle, which I've tried to draw here. And then I need to tell you a configuration of n marked points on a standard National Bureau of Standards fixed theta graph. That's a point from here. And then I need to do that whole thing up to the 12 element automorphism group of the underlying graph theta. So the action of this group on the configuration space is induced in the usual way. And the action on the open simplex is via the action of the automorphism group on the edge set of the theta graph. So just to be clear, the S2 doesn't do anything on the open triangle, and the S3 permutes coordinates, permutes the vertices. So that's really the space we're studying, at least in genus 2. So one can prove then that, so this identification allows us to rewrite the reduced homology of delta 2n as some kind of, the iso co-invariance of this reduced homology group of a compactified configuration space of n marked points on a theta. And this is twisted with the sign representation, which is exactly from the, so the sign representation on the S3 component of the isomorphism group of the theta, which is from the permutation action on the open triangle. So this -2 shift is due to the 2-dimensionality of that open triangle. So this is the way in which these two stories are related. And I was very happy to be able to make such a connection because, configuration spaces of graphs, I probably should have mentioned, have this long history. They're studied from many different viewpoints. For example, from the robotics viewpoint. So you can see the work of Robert Grist, for instance, I think. So in robotics, in actual applications, so I'm told, one has a situation where you have robots going around in some kind of factory floor doing things. But of course, they're not just moving in a 2-dimensional parameter space. They usually have some 1-dimensional constraints, some tracks that might meet. So these tracks are some kind of graph. And then these robots have to get around each other. And so this is exactly studying configuration spaces of points on graphs. There's a lot more to say about stability phenomena and so forth. So there are papers of many authors, including Aaron Abrams, Eric Ramos. But the study of compactified configuration spaces is a bit different. It has a different flavor. But this is I think, a compelling application. Okay. So let me see. So throughout this, so we've gotten to this point of the story. Now the question is, how do you compute homology groups of compactified configuration spaces of graphs, and ideally SN equivariantly? So let me use the time. Okay, so let me use my remaining 0 minutes to give you a quick sense.
And take a few more minutes if it works.
Okay, thank you. All right. So the first thing is that the compactified configuration space is actually like a homotopy invariant. It's invariant under proper homotopy. So in particular, you can actually pass to your favorite genus G graph, which should be the rows on G petals drawn on the right. then we show that the rows on G petals, its compactified configuration space, has homology computed very, very cleanly by just a two-step chain complex. And this is a chain complex that is consists of free ZSN modules. So it's free on a bunch of regular representations. And we have a combinatorial formula for this boundary. So that's the main, I think, this is the gateway towards more efficient computations, as I'll explain in my remaining -1 minute. Oh, and we need to be able to control the way that the automorphism group of a given graph, like for example, theta, acts on this chain complex. But you do so by sort of expressing that action via the action of the outer automorphism group of FG on the homology. So we can realize this action on an appropriate generating set of out FG on the chain level. I'll skip the definition or the recollection of a canonical set of generators or a set of generators for out FG. So that's how we do the computations. Now there's one trick that I wanted to advertise. If you want to fix a single irreducible representation and compute its multiplicity in the homology, that is to say the kernel and co-kernel of this map, you can do so in a highly efficient fashion. And I will be completely open that I learned this trick from my collaborators. So here, the map we had, it's a map of ZSN modules. So it's expressed by a matrix whose entries are elements of the group ring. So formal sums of representations. And the trick is that if you want to just single out a single irreducible representation, then it follows from the Peter-Weyl theorem, as you can see our paper, that you can isolate that representation and its multiplicities by taking instead a matrix obtained from rho, your representation, and from rho and from delta, your differential. So you take your matrix whose entries were elements of the group ring, and you replace each element of the group ring with the associated D by D matrix associated to the representation. Then you have a matrix of matrices. You flatten it out by erasing the parentheses, and you get a matrix that computes the multiplicity spaces of these irreps, the kernel and co-kernel. This is the trick that makes the computations go quite so much further than previous methods allowed. Okay. I think I have to stop there. Sorry for going over, and thanks for your attention.